Hi, we're going to move on to chapter 7.2, which is the shear and moment equation and diagrams. Yeah, so we'll be trying to draw the shear and moment diagrams for beams and other structures. Yeah, so beams is structural members designed to support loading perpendicular to the axis. Like example, this is a beam. Yeah, a simply supported beam is pinned to one end and roller to the other. There's a pin here and there's a roller. Now, why do we have a roller? Because if let's say in a hot temperature, hot environment, this beam will expand. So if you have a roller here, so it's not fixed. Yeah, so what happens is that it allows certain amount of movement for the expansion and contraction. If it's cold, it will contract, so it will move back to become slightly shorter. So that's the reason why you have a roller at an end. And a cantilever beam is a fixed at one end and free at one end. So cantilever beam is actually mostly embedded inside the wall. So you literally cannot see this part, yeah, because this is within the inside the wall. Yeah, so it's a bit different because there is no any pin support or something. It just looks like something that is just protruding out from the wall. Okay, so let's move on. Okay, what is the analysis? We have to find all the reactive forces and couple moments acting on the beam. So that's the first part, to do all the the whole free body diagram, and then specify separate coordinates for x. Yeah, and then we have to do what you call let's say you have the whole beam, yeah, a long beam. Next, you have to break them up into, okay, first part, then second part, then third part. You have to go longer, so that depends on the forces itself. Wait, I'll show you shortly. Yeah, okay. And the last one is to plot the v versus shear versus distance and moment versus distance. So mostly both these graphs are actually in one line. They are all in one line because whatever changes that's happening here will affect the changes that's happening down here. So it's in one line. Okay, you understand? So most time we draw in one line, something like this. Here we have the v and then we have the moment. So this distance and this distance will just follow the same thing. Okay, you understand? Yeah, okay, let me just show you some example here. Once again, we'll be skipping the example from the class exercise because it's a bit simple, so I will straight go to the textbook, a more complicated example. Yeah, okay, so let's look at this. So we have draw a shear and moment diagram for the shaft in figure 7.11a. The support of A is a truss bearing. So this is a truss bearing, and support at C, this is a truss bearing, and the support is C is journal bearing. Yeah, okay. So we know that bearing has got only one unknown force. Yeah, so the first step is to, in this example they didn't actually show to solve the whole free body diagram. So what you need to do is you need to draw and find the what do you call the for the whole free body diagram. Yeah, so in this case your whole free body diagram would look something like this: cy and ay. So this is a force of 5. So looking at this, the distance is 2, the distance 2, automatically this is ay. Now I'm a lecturer, it's okay for me to write that this is 2.5 kilonewton, but unfortunately in the exam you need to show the full working. I repeat, in the exam you need to show the whole free body diagram, solve for the unknowns, and you have to let me know how did you get 2.5 in detail. So I'm going to skip that part and I'm going to straight go to drawing the shear and moment diagram. So we know that this is 2.5. So you see, you look at this structure. So what we're going to do here is that, yeah, so what we're going to do here is that we're going to break it up. Yeah, we're going to break it up. One second, my eraser is not coming out. Where's my eraser? Okay, eraser is working. Okay, I'm going to break this up, which means, you look, the force is actually, something is happening at 5, right? Correct. So I'm going to cut this from A to just before 5. That will be the first segment. The second segment will be A, from A just after B. So we have going to have two segments. Why is that so? Yeah, why is it so? Because you see, when we want to plot our graph, we know that if there is an external force, there's something changes going to happen. So your external force is at 2, right? Something that's happening, and then we have at 0, and then the end of it is actually 4. So this is what our main aim is. Yeah, at 2, at 4, and then this is your moment, and this is your shear. Okay, you understand or not? Yeah, so we have to cut the segment for segment, the first segment. So in the first segment, what do we have? We have the 2.5, which comes from the free body diagram, and then we call the distance x. So what is this x? X is just below 2 meters. Yeah, just below 2 meters. That's why you see down here, can you see? X is between 0 to 2 meters. Yeah, x is between 0 to 2 meters. So the first set of equation for this segment, this is the first set of equation. So we have Fy equals to 0, where V is 2.5. And then we have moment, so there will be moment at this point here, that will be 2.5 multiplied with x, 2.5 multiplied with x. So if you see, this is the reason why we have kept it in x form, because we want equations. Yeah, we want equations in order to plot the graph. So what's happening 0 to 2? Between 0 to 2, the V is actually 2.5. So you have 2.5 here. Okay, that's the 2.5. So the V would be a straight line, nothing is happening until 2. Until 2. Okay, so this is how it is. Okay, so we have 2.5x. So 2.5x at point 0, it is 0. Yeah. At point 2, this will be 5. So it means the maximum that it goes to is 5. So you draw a straight line, something like this. You get it or not? So that will be the first segment. Okay, you have done for the first segment. I'm going to change the pen to another color to look at the second segment. Okay, the second segment you have taken a bit longer after B, right after B, but before the C. You get it or not? So we have A, B, and just before C. And the distance would be, the x would be between 2 to 4. Between 2 to 4. So we have 2 meter here, and what is the distance here? X minus 2, because the whole thing is x, and this segment is x minus 2. Okay, so now let's solve for the, so for this drawing, this is the calculation. Okay, so if you look at Fy, what we have here? 2.5 pointing up, negative 5 pointing down. So V is negative 2.5. So what does it mean? From distance 2 to 4, the V is actually negative 2.5. So it will be somewhere below here. So finally the graph will look something like this. Okay, just like that. Okay, this is for the V graph. Yeah, V graph. We haven't settled for the M graph. Okay, now we are taking moment at this point here. So when you take moment at this point there, what we have here? We have M, moment here, equals plus 5 multiply x minus 2. And then 2.5 multiply x. So when you have that, you have an equation of 10 minus 2.5. So how would be 10 minus 2.5? Yeah, the sloping would be from 10 coming down. That would be 10 minus 2.5. The slope is negative 2.5x. Yeah. Okay, let's look at the answer. Can you see the answer? Yeah, it's similar to our calculation. Any intersection at 0 will be maximum at M. Any intersection 0 in V graph will give a maximum in your M graph, either a positive maximum or a negative maximum. It depends. Yeah, it can be positive or it can be negative. It depends. Yeah, so this is how the graph has been plotted for this. Okay, so I hope you understand. Yeah, you just have to repeat this, then you'll be all okay. Okay, let's look at these then. It's a bit more complicated because even here itself, it is actually in a distributed load. It's a triangle, you see, it's a triangle, and it is 6 kilonewton per meter. 6 kilonewton per meter. So they want you to draw shear moment diagram for this beam. Yeah, looks very simple, but then it's extra work because this is a what you call evenly distributed load. So looking at this, this is a pin. You have one unknown, two unknowns here, but in this case, your maybe you want to give the name A, point A. AY will have a value, but AX will be 0 because there is no any horizontal values here. And then we have here, we have one value. So remember, even before you actually do any question progress further, you first have to solve for your whole free body diagram. Whole free body diagram. You must solve, yeah? And then when you cut something, you have to cut from the left, move to the right. It means I cannot plot a graph from this side. I always have to start plotting a graph from my left to my right, right? You don't plot the graph from, this is a graph. You don't plot from here to here, right? You always plot from here to here, isn't it? Correct or not? That's what I'm trying to say. Okay. Okay, let's look at how to solve this question. Okay, let's look at the first segment. So the first segment, because since that there is no any external forces along this line, yeah, so what we can do, we can just cut anywhere. So your x can be here, your x can be here, anywhere, yeah. So we have just taken a value x, which is not 9, but somewhere below 9, yeah. The x will be in between, x will be in between, equal to in between to 9, yeah, anywhere in between, yeah. Okay, so the diagram will look like this, some 9 here. And then when we cut, we're exposing the V and the moment and normal, but in this case we don't draw the normal, yeah. And then we have one loading here, which is half times base times height, half times base times height. So if you're calling a distance of x, yeah, and here will become 2/3. How did you get 2/3 there? Yeah, let's look at the similar triangle here. This is 6, this is 9, correct or not? Yeah. So if you call this x, similar triangle, if you call this x, what is the ratio up here? It will be 6/9x, isn't it? Correct or not? Yeah. So it means, in another word, it will be x, and this will be 2/3 x. So that's how it is. It came up to 2/3 x, yeah. So half times base times height. Half times base times height, you get 1/3 x square multiply with 1/3 of x squared. So how did you get that? You see, you have half times base times height, 2/3 x. So what do you have here? 2, 3, and then you have 1, 3 x squared. Got it? So that's how you get this value. Okay. Okay. So if the distance, you put your force here, this will be 1/3, right? That's understood from the very beginning itself. So now let me just erase this whole thing and then rewrite it neatly for you so that you can understand the whole thing. Okay, so you can see everything clearly. Get back to the pen. Okay, so Fy, we have 9, and we have 1/3 x squared, which is coming down, and we have minus v, yeah, minus v, which is pointing down, equals to 0. So solving this, it will form an equation. Can you see that? That's what our main aim is. We want an equation in order to plot a graph. Yeah, that's the reason why we keep it an equation. Yeah, sorry, the thing just moved. Okay, that's why we keep an equation. Okay, the next one is moment. You take a moment here. So what we have? We have 9x, 9 multiplied with the x distance. We have the existing moment, and we have 1/3 x squared multiplied with x over 3. Yeah, positive minus depending on the rotation. This will go clockwise, which is negative, and this will go anti-clockwise, which is positive. Yeah. Okay, so leaving you with this equation, m equals to 9x minus x3 over 9. Okay, so with that, you got two equations. Now you have to draw a graph. Okay, like drawing a graph like this, you need to know what is the intersection. You know how to draw a graph, right? That's your maths lesson. You plug in 0 here, so it will get at 9 here, right? One plot here. Okay, and then you need to know where is it intersecting at 0. So this is the working. At 5.2, it will intersect at 0. So you make this one as 0. Yeah, v as 0, and then you find for the x. So you get at 5.2, it will come to 0. And then at distance 9, so you plug in here, 9 square over 3 minus with 9, what you get? You get negative 18. So that's how you plot the graph. Now remember one thing when I told you, when the intersection here is at 0, it would be a maximum or a peak at the moment graph. It can be a positive peak or it can also be a negative peak, so we don't know, but it would be a peak. You understand what I'm saying, you know? So that's why you need to further calculate. Yeah, and if you see this example, can you see they have actually plotted in the same line? Okay, so distance 5.2, you can anticipate it's going to be a peak, but we don't know whether positive or negative. So once again, you plug in 0 here, yeah, and then you can get what? 0. You plug in 0 is 0, and then you plug in 5.2 because we know it's a peak, right? At 5.2 is 31.2, so 31.2 will be maximum because it's a positive value. So you know your graph will hike, yeah, will hike up here like this. And at 9, what happens at 9? 9 times 9, 9 cube over 9, so it becomes, wait a moment, oh, it brings down 9 power of 9. Okay, it means it's a 0. At distance 9, it comes down to 0. So you know this is the shape of the graph. So you just need to plot. Okay, so in exam, it's very important to show this value. Let me just erase the whole thing and tell you what are the values that's very important in the exam to be shown. Yeah, otherwise you'll not get marks. Yeah, this value, this intersection value, this maximum value, what is the initial, what's the initial. The equations are very important. The equations are very important. This is how it is being done in the exam. Yeah, and you need to draw them all in one line to show the variation of the forces itself. Okay, so that's what I expect from you from the exam or your test. Okay, good luck.